have amplifier designer David Berning. He's joining us from LTA, which is linear tube audio, and he's the architect of the Zero-hysteresis Output Transformerless architecture, which is a modification of the original OTL design. So he basically took that design, enhanced it, and that architecture is used in the LTA products to this day. So also on the call we have Mark Schneider, who's the CFO. I'm sorry, the president of LTA. And I was hoping to also have Nicholas Tolson on the line, but he can't make it. But today, David's going to give us a presentation of the overview of the history of OTL and his architecture. And I'm looking forward to that because I'm interested in his new headphone amplifier that is able to power Stax headphones. So I'm interested in his presentation. So with that, Mark, do you want to tell us a little bit about LTA and how you got it started?
Okay, well, about 8 years ago, we had a mutual friend, David and I, and David he made some custom amplifiers for this guy's custom. He made his own electrostatic speakers. Anyway, so we I had some little amplifier I wanted to make, and he said, well, instead of trying to make that amplifier, why don't you try this amplifier, which I made a few years ago, and I got a stack of letters with 100 people begging me to make another one. So I said, that's a great idea. Let's start with that. So we've been working together. We have about 10 people. We're in Tacoma Park, Maryland. All of our amplifiers are either straight David ZOTL circuitry, plus we make the cases and some of the volume controls and the things that go around it. And there are some other devices we have that aren't ZOTL, but there's still a lot of David Berning technology, if you will, because he taught us pretty much most of our technical knowledge is derived from David, because it's generally a little different than most of the other classical tube designs. David did invent the ZOTL, not just update it. It came all out of his brain. Anyway, it's a very interesting technology. It's not, as David will explain, has nice benefits like 3 times the tube life, 1/3 the heat, twice the voltage swing. So anyway, it's enabled us to really provide something that's higher quality, sound quality than you typically get in much more expensive amps at a much lower price. So anyway, I'll turn it over to David because he's the brains behind the operation and he's much more interesting to listen to. Go ahead, Mr. Berning.
Okay, let's see if I can make this work with the shared screen.
We see you fine.
Well, do you see my screen? I don't see it.
No, the screen is not there.
Oh,
there it is.
There it is. Okay.
Now it's full screen. Perfect.
Okay. All right. Let me see if I can get rid of this little thingy on the side there. Yeah. Okay. Okay. The title of my talk is The History of Output Transformerless Tube Amplifiers, known as OTL. I originally gave this talk for the Bowie Museum of TV and Radio. Anyway, this is modified a little bit to be for an audio group. Anyway, the output transformerless amplifier was basically developed at the beginning by Futterman. But before I get to that, why output transformerless? Well, typical tube amplifiers, vacuum tubes like high voltage and low current. Speakers need high current at low voltage. And so they don't really talk to each other very well. So the traditional way of solving that problem is to incorporate a coupling transformer. And the coupling transformer, if you use a small one, you get small sound. If you want full hi-fi richness, you have to have a big, expensive, heavy transformer. So anyway, here's the outline of my talk. Futterman develops the output transformerless amplifier purposed for audio hi-fi. Then I'm going to talk about Futterman licensing his OTL amplifier to New York Audio Labs. And this increased visibility tremendously. There was an explosion of small companies making OTL amplifiers. Then I'm going to talk about the Berning ZOTL amplifier, how it works. And this gets kind of technical in places. And then I'm just going to finish up the talk with a quick section on the OTL and single-ended implementation, which is fairly rare. But anyway, it does. I found a few examples. Julius Futterman is considered the father of the OTL. Born in New York as the descendant of German immigrants, he died in 1981 in New York. Prior to his work on the OTL amplifier, he was employed designing tube testing apparatus. And this gave him a big advantage in understanding important tube attributes that would best suit building a transformer, output transformerless amplifier. This is this shows his 1956 patent. The summary of this patent, it relates to amplifiers and particularly to audio frequency power amps employing large amounts of negative feedback to reduce distortion and is therefore useful in the reproduction of speech and music. Just a little word about negative feedback in tube amplifiers. With the traditional amplifier, with an output transformer, it's very difficult, in fact impossible, to apply much negative feedback. And thus very difficult to get the measured distortion. And I emphasize measured distortion low. Tube amplifiers with output transformers have never been competitive with high feedback solid state amplifiers. And the reason for this is, and I'll actually get into this a little bit more detail, but the transformers present horrendous phase shift issues, and so you really can't get much more than maybe 20 dB of negative feedback in a transformer coupled amplifier, whereas the Futtermans had a lot more than that. Now, I won't say anything about sonically what that means, because there are a lot of varying opinions. Feedback's good, feedback's bad. There's as much argument about that as there are audiophiles. But anyway, I can sort of point in some directions of what might be important. This is a original Futterman schematic of his first amplifiers. There's some interesting, and since this I understand is a pretty technical crowd, I'm going to talk about this a little bit. First of all, the thing that struck me is note the lack of safety isolation from the power line. He's got a direct connection from the 117 volts to the power supply, which feeds the output stage. that powers the filaments for the output tubes. Interestingly, it's got a power transformer for feeding the input tubes, but the output tubes are not protected, so you, the user, are not protected from getting a nasty shock from from the line voltage. But aside from that, there's some very good design in this circuit. There's essentially no voltage gain, and probably there's voltage attenuation in the output stage. And there's no voltage gain in this phase splitter stage either. All the voltage gain is in the first stage. And this topology offers some really important advantages if you want to apply a lot of feedback. The impedances in all this part of the circuit are low, and so the bandwidth is going to be quite high. The first stage has open loop lousy bandwidth. You've got a pentode, which is very high impedance. It's fed with essentially a current source, a very high 1.8 mega ohm resistor. You've got one dominant pole in this amplifier, which is very clear. It's the Miller capacitance between the plate and the grid of the second tube. I said I was going to get technical, so I will. If you were designing a modern day op amp, this is the kind of the ideal way that you would go about it. You want that dominant pole so that you can get very, very high stability. And that's the key to being able to apply a lot of negative feedback, is you have to have that stability, and you have to have that single dominant pole and no other screwy things in the circuit to affect phase shift anywhere near where that dominant pole is working. And if you study the circuit, with that in mind, you can see that, hey, this is actually pretty good. So let's move on. This is a timeline of the Futterman amplifiers. The 1959 offering is based on the patent, with 4 of the 12 BH or B4 triodes in parallel for the high side and 4 more for the low side. It was monaural with about 10 watts. The 12B4 is a vertical deflection amplifier with plate resistance of around 1,000 ohms and an amplification factor of 6.5. Later, Futterman offerings such as the H3 and the H3AA use various beam horizontal sweep tubes, and finally ending with the 6LF6, which is a very, very high performance tube. I've used it myself over the years in my amplifiers. When New York Audio Labs licensed the design from Futterman in or about 1981, which incidentally is about around the time he died, or very shortly before the time he died, I think, they were able to continue without too many changes, except for cosmetics and putting it in a fancier box and whatever. But New York Audio Labs was fairly short-lived. The Black Monday stock market crash in 1987 ended a lot of high-end audio companies. And I'm not sure, but I think that probably was, what happened to New York Audio Labs in part anyway. A discussion of the history of output transformerless amplifiers wouldn't be complete without at least mentioning what Philips was doing. They made hi-fi amplifiers, but the interesting thing about them, they were output transformerless, but they were designed to go with a special Philips speaker, which was high impedance. It had about an 800 ohm voice coil. And it's a little diagram on the back of the amplifier showing, connecting probably a woofer and a tweeter. I guess that's what that means, to the amplifier. But Philips also had made quite a few consumer items like radios and even television sets with output transformerless tube amplifiers in them. But I just wanted to mention this. I'm not going to go into any more detail about it. But let's move on to the Futterman licensing his amplifier to the New York Audio Labs, and that increased the visibility. So this is what the early New York Audio Labs, well, actually, it's probably what they all looked like pretty much. And Harvey Rosenberg was the main guy here who started this, and he had a few other players on his team, John Snyder, or Sider, I guess it is, Ted Hammond and George Kay. So they licensed the Futterman design. They made several versions of this, OTL 1, 2, 3, 4. This is kind of what the innards look like. Some of these were, I think, mono, some stereo. Some had a separate power supply like this one. But, they gave Julius Futterman the credit. His name is on the faceplate. Julius Futterman OTL amplifier. Harvey Rosenberg, he's the one on the right. He's a very significant player in advancing the OTL amplifier in promotional terms. He was a very colorful character, known for wearing kilts at hi-fi shows. He was largely responsible for taking the OTL concept out of the cult status to having extensive publicity in the audio community. You see him here with a strange headdress that included tubes. Unfortunately, he died at age 59 from a heart attack on an airplane. His headdress with tubes, this probably was taken after New York Audio Labs. I'm just sort of guessing because Harvey got into low power triodes, 2A3s, tube rectifiers, things that would not have been in his OTL amplifiers. And he's showing this off in his headdress. And I just, Harvey had like, it was like a cult in a sense. And so you have your triad fathers, and I just, have to, I don't know if you can see it, but I have his T-shirt as well for the triad father. So it's, and as a result of his getting everything going, there was an explosion of small companies making the OTL amplifiers after Harvey got out of that. I'll just go through with a slideshow of eye candy, some of the different companies that I found that were, making, interesting looking stuff. Jewel Electra, they used a 6C33 low mu voltage regulator tubes from Russia. A lot of companies use that tube. Not very linear, but they, it's hard to beat them for, high current and low impedance. And so you still need to put a bunch of them in parallel, but not as many as you would for if you were doing some of the early Futtermans with the 12B4 and whatever. Tenor, again, they use the same tube. Now this ITOS, they used the TV sweep tubes, probably EL519 would be my guess is what these are. And Einstein, they used the Russian tube again. Graph, I'm not sure what tube they used. It looks like they have plate caps, so this is probably a TV sweep tube as well. But for a 200-watt amplifier, you can see there are a lot of tubes. This looks like a stereo amplifier, but nonetheless, there are a lot of tubes to get 200 watts. One of the better earlier players was Counterpoint. They used TV sweep tubes, a 6LF6. They showed quite a few years at the hi-fi shows. Probably you've seen them, or you saw some of these amplifiers. This one I'd never seen, but I ran across it. 27 output tubes per channel. It says reference 200. It's probably 200 watts per channel, would be my guess. But you can see how absurd that the OTL thing can really get if you try and get a lot of power out of them. You just have to parallel an awful lot of tubes, and that's an awful lot of power consumption. Here's another one which I'd never heard of, but I don't know whether this was intended to be used in a theater setting or just what, maybe a shaker table. Maybe it had nothing to do with audio. I don't know, but it says left and right, so I guess they were used as audio amplifiers. And probably the best known OTL amplifier maker is Atmosphere, and they have a fairly broad number of different models that they make. But again, when they get up into the higher power, like the MA3, you got a lot of tubes and a lot of tubes to maintain, and it can fail and whatever. Their favorite tube is the 6AS7, which is a low mu dual triode. Again, these tubes are designed as voltage regulator service. They're not all that linear, but they are relatively low in impedance, and that's why they're favorites for people making OTL amplifiers, particularly ones with low feedback. When you use the beam power tubes, you need more feedback to bring the output impedance down. With the low mu triodes, you don't need so much negative feedback to get reasonable output impedances. It's not going to be real low, but it's going to be more reasonable than what you get with beam power tubes. Even this article by Tim Mello in Audio Express, he did a very nice article on his DIY 25-watt OTL, again using the Russian 6C33. Transcendent Audio makes OTL amplifier kits. They have a variety of products. So there are a lot of these, of one form or another that you can buy or build or whatever. Now this is a little interesting deviation from the other amplifiers I showed, which were really unarguably OTLs in their purest sense. This amplifier, it hits all the right buttons. It claims to be OTL. It claims, pure Class A, output transformerless, 300B single-ended. I mean, it hits a lot of things. And then you look at the specifications. Power output 250 watts into 3 ohms. Damping factor greater than 100. Negative feedback is non-existent. An output current more than 200 amps or more than 100 amps. Well, a 300B might have a current capability of 1/4 of an amp, maybe. So what's going on here? Well, this is what they're doing. They've got their 300B output stage, and then they're sensing the output current from that, and then they're obviously amplifying the heck out of it to drive their speaker. They're claiming that they have no feedback. They claim it's an all-tube amp. It's not a hybrid. It's not this or that. But I leave others to be the judge on what all that means. So I'm not going to go any further on that. But it just points out that there are some things that might stretch the imagination a little bit that are on the market. I have no idea how this sounds. It might be wonderful. It might not. I don't know. Now I'm going to talk about the work I've done, the Berning ZOTL amplifier. First, let me just say how this got started. It was kind of strange. I was trying to do a switching amplifier using resonant power conversion technology, or the technology I'd used in my power supplies, that I'd used in my switching power supplies when I was still doing transformer coupled amps. And so I was trying to use frequency modulation to control the output of a switching type amplifier. And my idea behind this was to circulate the full current all the time. So, you stayed away from, crossover notch problems, crossover distortion, things like that, because you'd be circulating the full current all the time, but you'd be returning it to the power supply continuously. So it wasn't dissipating a lot of heat. So I was trying to make this work, and I actually did make it work, but it wasn't working in an acceptable way. There were little glitches on the waveform, which you had to look closely on an oscilloscope to see them, but you could hear them quite easily. There were little buzzy things, and they were the result of diode recovery. And I kind of came to the conclusion that, yeah, this isn't going to work. So I gave up on it, but in the process, I stumbled across using, some of the same ideas, but using a tube as a load in a linear fashion on a switching converter thing, and it seemed to work. And so I pursued it, and I decided, well, I got this office Christmas party coming up, and I always provide, I work for the government, the National Institute of Standards and Technology, National Bureau of Standards at the time. And so I said, yeah, I have to, provide the music. So I'm gonna build an amplifier out of this wacky idea I have. And everybody's gonna be drunk there, and they're not going to be able to evaluate whether it sounds good or bad. And so it really doesn't matter if it sounds bad. I mean, it's just having a little tube amplifier that I can make physically very small. Yeah, it'll just be interesting visually, and it'd be small and light because there wouldn't be any big transformers on it. So I built that amplifier, and I listened to it, and I was shocked because I thought this was just a joke, and to me it was a joke. When I made it, and I decided that I pulled out some records that I'd listened to that I was very familiar with my normal transformer coupled amps I was making at the time, and there was one record I had in particular, Shostakovich String Quartet. I could get two of the instruments to sound right on my transformer coupled amps, but I could never get all four of the instruments to sound right. And I could change things, and maybe I'd get one of the other instruments to sound convincing, but I'd lose one of the other instruments. So it never really was a convincing reproduction of that very, very difficult record. So I played that record with this, this crazy thing I just built, and lo and behold, all the instruments sounded right to me. And I couldn't stop listening. I just, listened all night, and ultimately decided, I've got to pursue this. I, patented it, and, went on from there. But getting back to Harvey Rosenberg, he writes shortly before his death, the amplifier I'm writing to you about is a different amplifier than the push-pull amplifier, which uses video compact drawn tubes that Dick Ulster reviewed. That, by the way, was the ZH270 amplifier that Dick had reviewed. I think he might have reviewed some other ones, but I know he reviewed that one. Anyway, Harvey goes on to say, this amplifier exists because I begged David to make the world's first 300B single-ended ZOTL amplifier so I could claim direct involvement in this historic achievement. Never underestimate the value of narcissism. We would have the new answer to the question, what is the sound of one 300B clapping? And this amplifier is an impossible dream come true. It is the convergence of the best aesthetics of OTL and single-ended directly heated triodes in a single circuit. If you can tolerate only 5 watts, it is the 300B single-ended version of the ZOTL circuit. Harvey coined the term ZOTL. I called it the Zero-hysteresis OTL amplifier. At the time, there was a lot of back and forth in the forums about, me calling this an OTL amplifier when it had transformers in it. They weren't output transformers, but nonetheless, there was a lot of bickering going on, and Ralph at OTL was one of the primary ones stirring the pot on that. As he was, of course, he was defending his traditional way of building an OTL, and this looked like maybe it was kind of a scary thing that I could do something with just a single tube or a single pair of tubes instead of having large banks of tubes. But nonetheless, Harvey came up with the idea, because Harvey was a very strong supporter of me at this time. He'd gotten out of the New York Audio Lab thing at this time, and he was into the low power triodes. So he was really promoting what I was doing, and so he wrote quite a few articles. He had them on his website, and this particular one was, and always funny, what he comes up with, like Dr. Gizmo abducted by aliens while eating deli. Anyway, it's Harvey. So now we're going to get into the nitty-gritty technical stuff. So the ZOTL amplifier, the fundamental thing about the ZOTL amplifier, basic principle operation, is based on DC to DC power conversion. So I'm going to just give you a real quick lesson on a real simple concept in power conversion to get things going. So let's look at this part of the circuit. Switch 1 through switch 4 form a full bridge made up of MOSFET power switches that are alternately commutate the applied DC voltage to the primary of the transformer, first in one polarity and then in the opposite polarity. This applies AC to the transformer that can be stepped up or down in voltage. The secondary AC voltage is converted back into DC voltage for the load by the full-wave bridge rectifier. In the ZOTL, that load is a vacuum tube modulated in conductance by a varying audio signal. So let's look at this. Switch 1 is closed, switch 4 is closed, 3 and 2 are open. So for this scenario, the voltage between the plus V and the return is applied in a polarity across the primary winding of this transformer, V plus to return in that polarity. The output of the transformer, you just get a square wave, and I call this phase 1. In phase 2, now switch 3 is closed and switch 2 is closed. So now V plus is applied to the transformer with the V plus on this side and the return on this side. So that gives you the opposite or the opposing phase, which fills in the square pulses on this side, out of phase from that side. You combine these two with the bridge rectifier and you get just DC, straight DC. Now this is all ideal. I'm not showing any parasitic effects or anything. This is just ideal, but it's not far off from the truth. It's just, it is ideal. So the voltage you get at the output is simply the turns ratio N2 divided by N1 times the voltage that's applied. So that's just the most fun. There are many different topologies of DC to DC power conversion, but this is the one that I use in the ZOTL. This is the patent that was issued to me in 1997 that covers the ZOTL. And I'm just going to read a little bit of the abstract. A linear audio amplifier includes a push-pull pair of vacuum tubes operating in a linear amplification mode coupled through a pair of DC to DC switching power converters to an external load impedance. Each power converter includes a transformer with one or more secondary windings that drive rectifier circuits, and the resultant DC voltage sources are loaded by their respective tubes. I'm not going to read the rest of it because it just kind of details how it's done. But so this is like a push-pull type of scenario. You've got a tube up here which is fed up a signal in this polarity. These are your 4 switches that I mentioned earlier. These are your rectifier circuits. And I use multiple rectifiers, not just one, for reasons of speed and you can't get, the fast rectifiers at high voltage. Not only are they not really available, it's the parasitic capacitance in the windings and parasitic inductance, which limits your bandwidth if you try and do this all with one rectifier bridge. So there are a number of them in series to be able to really implement this correctly. And this part would be like switch 5 through switch 8. This is the negative half. The tube on the bottom gets the inverted signal. So these combine, they're in series. So you got what I call the high side tube, high side whatever. This is the low side, and then you got your 2 power supplies in series that power this, and the center is just coupled to the return. The center tap of the power transformer is coupled to the load return, and then these 2 are joined in series, and that series connection is your output to your speaker through a noise filter, which is optional. But I always use it, but you wouldn't have to. The important thing about this is one of the important things about it is there's no power gain in the impedance matching process. That's important. It's not a hybrid amplifier, which would, that would have power gain in the output stage. This is different. And I'll show you why it's different later on in other ways too. So let's talk about how the tube controls the speaker in the ZOTL. Let's look at this half of the circuit, half of a push-pull circuit. Alternatively, this could be the whole circuit if you want to use a current sink on your speaker to use for a single-ended application. But let's just forget about that right now and just consider this half of it. So note, the V plus voltage is applied to the series combination of the commutating voltage, or the commutating bridge, and the speaker. So we have the commutating bridge here and the speaker here, they're in series. So only the portion of the V plus across the bridge is modulated by these MOSFET switches and applied to the primary of the transformer here. The remainder is unmodulated and applied to the speaker only. So you've got the voltage across this part of it modulated. You got the voltage across this part of the circuit, which is the voltage across the speaker, that's not modulated. So the plate to cathode voltage on the tube is described by this. It's the V plus minus the voltage on the speaker, and that's what you're going to modulate, times the turns ratio of the transformer, which I'm going to say is now going to be demodulated by the bridge. So that's going to be your plate to cathode voltage on the tube. As the conductance of the tube is modulated by the audio signal, the conductance of the MOSFET commutating bridge changes accordingly by loading through the transformer. This modulates the audio frequency voltage applied to the speaker. So let's just say the tube turns on, let's say it turns on hard, shorts out. Let's just say it shorts out. That prevents a short circuit, or presents a short circuit here. So it shorts this part of the circuit out. So that applies the plus V directly to the speaker. So you have full voltage that's available from your power supply up across the speaker. So that would be your maximum excursion on the speaker in the, say, the positive direction. So, as you can guess, that any state of this tube in its conduction, anywhere between being a short circuit and being cut off, is going to, make the voltage across this full bridge change, going from a situation where you have all your voltage applied across the speaker. If the tube's cut off completely, then this is basically an open your open circuit here, so no voltage gets to the speaker. So the voltage across the speaker is zero. All the voltage is across here, but it's not going anywhere if the tube's turned off. So let's look at the let's compare an output transformer, including parasitic elements, with the ZOTL. So let's start with the output transformer. And so this is a push-pull case. I've drawn in some of the parasitic elements in their simple forms. These elements that I've drawn in, the leakage inductance, the parasitic winding capacitance, these are all distributed parasitics. So they're more complicated than what I've actually drawn here. But you get the idea that these parasitic elements are interfering with ideal operation of this transformer. This inductor over here represents the magnetizing current, and that limits your low frequency. It also causes, you end up with saturation of the core. So that, these parasitics are kind of what fouls the output transformer. But forgetting that for a minute, the output transformer, what it does is it matches the high tube voltage or impedance to the low speaker voltage impedance, and that's the desired function that you need to drive a speaker from tubes. So this system, the power is fed in to the system from the primary side with the tubes at high voltage. So you got your B plus feeding your center tap, and so the tubes get their voltage from that. The bandwidth is limited at high frequencies by the leakage inductance that I've shown and parasitic capacitance in the transformer. The low frequencies are limited by the magnetizing current here and saturation. This is a simple AC coupling concept. Let's compare to the ZOTL. Let me just say the ZOTL transformer parasitics are not shown, but similar to the output transformer. The parasitics affects efficiency in both positive and detrimental ways, but do not affect the frequency response. But let's look at the differences. The power is fed into the system from the speaker side. Now I'm going to define that as a primary at low voltage. So this is now the primary. We're feeding our power in here and here. The high frequency bandwidth is limited by optional noise filters. I haven't shown any here. I'm just showing a direct connection. There's no low frequency limit to this whatsoever. It's DC coupled, goes down to DC. I mean, plain and simple. And it's a DC to DC power conversion concept. So here are some additional differences that are not related to normal audio reproduction, but they're worth just mentioning. Not that they, as I say, they don't affect the audio, but they're interesting, side, comments to make. The ZOTL will not impedance match to a signal at the same frequency as the carrier frequency. Most of the carrier frequency I use are 250 kilohertz to 500 kilohertz, somewhere in that range, usually toward the lower end of that now. But so if I'm using a 250 kilohertz carrier, I can't impedance match a signal which is 250 kilohertz. The circuit just, it fails. There are minor signal amplitude variations are present if those signals are harmonically related to the ZOTL switching frequency. In other words, if I have a frequency of 5 times, or say 3 times the 250 kilohertz, say 750 kilohertz, and you try and do the impedance matching on a 750 kilohertz signal, it'll do it, but you'll see a little ripple, a little dip in amplitude. And even subharmonics, you can see little, perturbations too. Again, these don't affect the audio. And this is an interesting thing about that. The ZOTL will impedance match signals higher than the switching frequency, unlike a digital system. As you may know, the digital system is affected by the Nyquist theory. You can't sample, you can't you can't reproduce something that's less than twice the sampling frequency, or the sampling frequency has to be at least double the frequency of the signal you're trying to reproduce. With the ZOTL, that's not a limit. You just can't do it at the frequency, but you can do it above if you wanted to. If everything else had adequate bandwidth, you could do it. Now, this is one of the most interesting, and this gets kind of technical too, reflected impedance. When you're considering an amplifier and you're driving a speaker, the speaker is it's not a resistive load. It's complex. There's speaker crossovers. There's back EMF. Back electromotive force and stuff like that can put power back into the the amplifier that's driving it in out of phase with what you think you're trying to drive it with. So how the amplifier, the active amplifier devices like the tubes, they respond to that because the tubes have transfer characteristics. And they respond to what's coming back through the transformer, and they behave in various ways depending on whether they're tubes or transistors or other feedback might be applied that affects it. It gets kind of crazy. So the concept of a reflected impedance is, okay, we're talking about what's going on with the speaker end gets back to the tubes. But I'm also, going to imply that there's transmitted impedance too. What the speaker sees when it looks at the tubes, what the speaker sees as impedance when it looks at the tubes, discounting any negative feedback that might affect that. But let's consider the output transformer first. So let's look at this case. I'm going to say, okay, we have an output transformer that's wound with a ratio on the primary to secondary of 10:1 on this coil and 10:1 on this coil. And these are in series, and the power is brought in at the center cap. And so, the tubes are, conventional push-pull, configuration. And the speaker is, loaded on this, the single winding output of the transformers, the speaker is loading that. So, so overall, we got 10:1 and 10:1. So overall, we got 20:1 ratio here, plate to plate. Plate to plate is a common terminology they oftentimes use when they talk about output transformers. Impedance goes as the square of the turns ratio. So the impedance conversion is 400. So an 8-ohm speaker presents 3,200 ohms to the series connected tubes plate to plate. In other words, reflected back through the transformer. The 8-ohm speaker is presenting 3,200 ohm load to the plate to plate connection of the tubes. But you can look at this in a little bit different way. The speaker presents 800 ohms to one tube at a time under Class B large signal conditions. So if one tube is cut off, say we got this amplifier under large signal conditions, and half the time one tube is cut off. During that period of time that the one tube is cut off, the speaker is going to present 800 ohms to the other tube under these large signal conditions. So anyway, it's kind of equivalent, but it's just another way of looking at something. Well, let's look at things a little bit different. Suppose each tube has a plate resistance of 2K ohm. Each tube reflects 20 ohms to the speaker through half of the transformer. So this half of the transformer, we present 20 ohms to the speaker. So the speaker say, from that component, the speaker saying, okay, I see a source impedance of 20 ohms. But under small signal conditions, both tubes are active under small signal conditions. So now these are in parallel because they're you've got your 20 ohms here and your 20 ohms here, but they really are in parallel for this treatment. So the reflected impedance to the speaker under those circumstances is 10 ohms. So let's see what happens with the ZOTL. So now we're going to look at the ZOTL. So the ZOTL, again, I'm going to do the same transformer. This is the high frequency transformer. It's not the audio transformer, it's a high frequency transformer. But again, I got 10 to 1 ratio and 10 to 1 in this one. So let's suppose again that each tube has a plate resistance of 2K ohms. So each tube reflects 20 ohms to its respective full bridge MOSFET commutation set. Again, we've got our this going is the square of the turns ratio, so our impedance changes by a factor of 100. So 2K ohms, becomes 20 ohms here. But we've got again, we got two of these in parallel because we got this in parallel with this one, even though it looks like they're in series. But under AC conditions, you can treat a power supply as a ground and a power supply as a ground. So these are actually in parallel when you consider AC conditions. So the impedance presented to the speaker from these 2K ohm, this pair of 2K ohm tubes, if they're both in small signal conditions, both active, is 10 ohms. Same as the output transformer. Under large signal conditions for Class B, one tube is turned off and its respective MOSFET bridge presents an open circuit. Then the 8 ohm speaker presents an 800 ohm load to one active tube through the active MOSFET bridge. Under small signal conditions, the 8 ohm speaker presents 3200 ohms plate to plate with an overall impedance conversion of 400. So, gee, it sounds a lot like the output transformer. Note that when the plate-to-plate configuration terminology is used, the tubes are in series as far as loading. Thus, each 2K ohm tube adds to make 4K ohms with an overall conversion of 400, resulting in a 10 ohm source impedance at the speaker like we had before. So this is kind of a mouthful of technical gobbledygook maybe, but the bottom line is it's saying that in summary, in the ZOTL under small signal conditions, the the primary, the converter transformers are in parallel, the secondaries are in series, the commutation bridges become part of the primaries, the bridges become part of the secondaries. Thus, the ZOTL becomes identical to the output transformer for the treatment of reflected and transmitted impedance. So that's the important thing to take home from this. Only the names primary and secondary switch places as power is fed into the system on the primary side. So this is very different than a hybrid amplifier where you're speaker is going to be looking at a transistor buffer, which is going to be completely different than what you have with your tubes. So how well does this work? So let's compare. Here's the 10 kilohertz square wave signal to an output transformer, a good output transformer. And yeah, there's some rounding and some things. The zonal impedance converter, now this is without an output filter. It's it's quite a bit faster. A curve tracer is an instrument that I use heavily to look at transfer characteristics of tubes. Helps in design, finding the best operating points, and so on and so forth. Some of you may have had experience with them. Probably most of you haven't. But for this graph, I did the transfer characteristics of a triode connected 6L6. And so the way what this is displayed per vertical division, you see the plate current, 20 milliamps per division here. The horizontal is plate voltage, 100 volts per division. So we got 1, 2, 3, and so on, 100 volts. This per step is the grid voltage steps size. So we start at 0 volts on the grid, and we go minus 10, minus 20, minus 30, and so on. And this is just your transconductance. So with a 6L6 and a triode configuration, if you look at this point up here where it's kind of like it's turned on as much as it's going to be, and you see for this condition you get about 200 volts plate voltage, and the plate current's going to be about 140 milliamps at that point. So yeah, that's not going to go very far in driving a speaker. You're going to have a lot of voltage drop across your tube if you try and hook a speaker up to this directly, and that's why transformers are used. That shows the real problem of trying to use a tube to directly drive a speaker. So with the ZOTL, I've taken a 6L6, a triode connected 6L6. Now I'm curve tracing it through the ZOTL impedance converter. So let's look at how the things have changed. The curves look pretty much identical. The shapes and all that kind of stuff is pretty much the same. But look at these factors. Now the effective plate current is 1, 2, 3, 4, 5, 6, 7 amps, and the voltage drop across the effective voltage drop across the tube is like 6 volts. So wow, now we got a very interesting amplifying device that has triode characteristics just like the triode. As I said, triode connected 6L6. But now I can drive a speaker with this real easily. Same per step voltage, the 10 volts per step. So that's the same as over here. But the these curves or these characteristics are really something that now I can work with to make a real amplifier out of for driving a speaker. And just for chagrins, okay, let's use a push-pull pair of 6L6s, triode connected and curve traced through an output transformer. So I've used a curve tracer in the AC mode, and curve trace through a transformer, and you get kind of a mess. You do the same thing through the ZOTL circuit, and all the goo goes away. The goo is, you get looping here, which is a mixture of hysteresis and low frequency limitation. This is hysteresis goo here. So none of that is present with the ZOTL. It's just much cleaner. I've used the same effective conversion ratio pretty much. I tried to duplicate this output transformer with the 200 milliamps per vertical division and the 10 volts per horizontal division. and same thing over here. So yeah, it does compare apples with apples, instead of apples with, something else. So what does a 200-watt Berning ZOTL look like? Well, it's all power supply, impedance conversion, and energy storage. Very little audio. I mean, it's just you don't have big banks of output tubes in parallel. It's pretty pretty simple audio path. And these are largely DC coupled. I have lots of protection circuitry incorporated in the power supply to cut back the power supply if you get DC on the speaker. But there's only one coupling input blocking cap really on the for coupling caps, and the rest of it's DC coupled with auto bias and all that stuff. But the impedance converters, this is the Quad Z amplifier, which has it's a monoblock, but it has actually two complete impedance converters that are operating 90 degree out of phase, and that's done to eliminate some of the non-ideal switching characteristics that are really present. It kind of fills in dead time, and it's not practical to do this in a kind of a lower powered amplifier because it's expensive. But if you're talking about a higher powered amplifier, it makes the more ideal power conversion a significant enough advantage to make it worth the extra cost. Power supplies, I use parallel resonance, not pulse width modulated, but it also does incorporate power factor correction, which is a pulse modulated circuit that's up here. So it's a universal line voltage amplifier that draws its power in sinusoidal waveform instead of high current spikes. So now linear tube audio has stepped up to the plate, and they're making things that are using the ZOTL technology under license from me, and but practical in price. The Quad Z is not very practical for most people, but linear tube audio is making a bunch of products which are pretty practical and quite nice looking. So I'm just going to do a little quick section on the OTL and single-ended implementation. This is kind of rare, but most OTLs are push-pull, but let's just look at it. Push-pull OTL amplifiers, they naturally supply both positive and negative current to the speaker. Generally, the peak positive current capability is the same as the peak negative current capability. Thus, it's a well-balanced drive to the speaker. And it responds well to speaker impedance dips and other goofy things that happen with a lot of speakers. Okay, so the single-ended OTL amplifier. Only a single polarity of current can be fed to the speaker from the active output controlling device or devices if there are a bunch of them in parallel. Some sort of current source is needed to supply the other polarity. You have to be able, if you're going to push the speaker in one direction with this one active output device, you got to have a way of pulling it in the other direction because speakers want to be pushed and pulled in two different directions. They don't just want to be pushed in one direction. So you need a source of current. You may need to store energy to do that. There are different ways to do current sources, and I'll talk about a couple of them. But moving on, the peak output current drive capability is generally much higher from the active controlling devices than from the current source. Thus, it's not a well-balanced drive. It does not deliver much power where you have a speaker impedance dip. That's why single-ended amplifiers really don't do well with speakers that have impedance that goes all over the place. And heaven forbid a standard OTL amplifier is going to do this horribly. So if you have a single-ended transformer coupled amplifier, usually the energy that you need to return the speaker and to drive the speaker in the other direction, you store energy in the output transformer air gap. That's why output transformers for single-ended transformer coupled amps have an air gap, generally speaking. Alternatively, instead of that, you can use a plate-loaded choke with an ungapped output transformer if you want to do that. But either of these above methods involves severe compromises between high and low frequencies. The single-ended OTL amplifier, it's rare, but they exist. They can use a large choke at low impedance, that is at the speaker impedance, to provide low loss current, a low loss current source without compromising the high frequencies. In the case of this where you're loading a tube at high impedance, the parasitics in either the choke or the output transformer affect in a negative way the high frequency performance of the amplifier. But if you can use a choke at low impedance, like at the speaker impedance, the high frequency problems aren't there because the impedance is low enough that they don't come into play. The low frequency ones do. The low frequency ones are equally problematic with all these, these effects. So there's no way around that other than just use a really big, heavy choke if you want to have good low frequencies. And another way to do it is use a transistorized current source. You have a lot of heat loss with this. So it's not an ideal solution, but it doesn't present theoretically anyway. There are no problems with it for performance-wise. I mean, it doesn't compromise high frequencies, and the low frequencies can be terrific. Incidentally, just as a takeoff on a little side thing I might mention to this, I've done this, and Westrex, the people that make the 300B, are doing it now in an amplifier that they produce, which is kind of a cross between a single-ended amp and a push-pull amp. But what they're doing, and what I did, is they're using a transistor. Well, I've done it with tubes as well, but they're using a transistor current source, but they're modulating the current source in such a way as to make it able to increase that current when you need it most and decrease it when you need it less. That basically allows you to double, at least theoretically or ideally, it allows you to get double the power that you get out of a dumb current source that's just operating at a steady state current. It may introduce some other things that are a little less pure, like you get more power supply modulation because it's more like a Class AB amplifier. But it really is, in a sense, a single-ended amplifier in that a single output tube is controlling the output waveform for the entire cycle. It's not being crossed over to another tube or the transistor current source, because the current source is high impedance, the tube is low impedance, so the tube is going to dominate the entire waveform. And so it really does meet the criteria of a single-ended amplifier from the standpoint of having one tube control the entire waveform rather than half of the waveform controlled by one tube and half by another. And then I used my Siegfried amplifier, which came out in the year 2000. I used a very interesting scheme to get the current source. I used a switching power converter operated at resonance for a current source, which returned the power, unused power, to the power supply. This wasn't ideal, but it was. It did go down to. It gave response down to DC, and it did, provide a reasonably constant current. It wasn't as ideal as a big choke at the higher frequencies. It did a lot better at the really low frequencies, but it wasn't as good as the high frequencies. So I haven't been using it in my recent designs, but it's just an interesting, different way of doing it. So why are listeners, with all this, why are listeners drawn to the single-ended amplifier with all its problems? In short, they sound so good. And lots of speculation on why. Single-ended output devices control the entire musical waveform without possibility of crossover distortion. There's less modulation demands on the power supply. But it really is difficult to back up subjective performance with measurements. So here are a couple examples of rare single-ended OTL, well, ZOTL compared with traditional OTL. The ARRI, this is no longer made, but this really is a single-ended kind of classical OTL amplifier. Power consumption was specified at 1200 watts. It's no longer made, but and then this is the amplifier we're currently making. Rick Brown is involved with making this as well. We're a team making this. So this is the reference monos that use the very, very linear 845 output tube, just one output tube. It can also take the 211. The power consumption on a pair of these is 300 watts, a factor 4 lower than the multi-tube in parallel approach. Interestingly, digging through the details of this amplifier, both amplifiers put out about 20 watts. Both use choke loading current sources, and both use about 2.6 amps for the current source loading. Now the ZOTL converts this 2.6 amps to roughly maybe, I don't know, 50 or 60 milliamps in the 845 tube, but the current going through the ZOTL is 2.6 amps. And this one, if you add all these tubes together, what they're claiming is that that total current that's idling through all those tubes added in parallel together is 2.6 amps. So that all makes sense. This looks like a genuine, product with no BS, and and of course my product has no BS. It's just expensive. So that's about it. There's some references here that actually include some of the old references I had on the Philips radios and stuff. If anybody wanted to, pursue some of that, they could see some of the circuits and the products that Philips made. Then just one final dash of eye candy. This is a $1 million horn speaker that one of our clients, one of Rick's clients, is using the Berning SET ZOTL to drive, including driving the woofer stack. It's driving the whole speaker, in spite of the fact that the speaker manufacturer does provide a solid state amp to drive the woofers. The option is there for driving the woofers with your own amplifier if you want to. So that's what this particular client is doing, and I'm told that the bass is kind of incredible. So that's it. So I guess we'll do the questions now.
Thanks, David. That's great. Got a few to start with, and then maybe we'll open it up for folks to just jump on and ask you. But one thing we've heard about is the lack of reliability on some OTLs. Can you talk to that a little bit?
Yeah, the let me turn the volume on. It's a little bit ringing. Yeah, anytime you've got a lot of tubes in parallel, you're going to have issues with reliability of, and this refers to the the general OTL. With the ZOTL, you don't have that issue with the multiple tubes in parallel, and you can design the thing so that it's using tubes in the way that they're happiest. That is high voltage and low current, where they're going to the cathodes aren't going to be destroyed by lots of current and lots of heat. With the high voltage, you get higher efficiency than what you get if you're trying to operate them at high current and lower voltage. So in terms of that's the chief thing that people talk about, I think, with OTL reliability is there's no transformer to keep DC out of the speaker. Some of the amplifiers do have coupling capacitors to protect the speaker. Most or many do not. So you do have liabilities there. And in the ZOTL, I incorporate, well, first of all, it's a controllable power supply. It's a smart power supply that can be shut down rapidly if something is sensed that's wrong. And with most of my higher power amplifiers, I have a couple different ways of looking at a failure. There's one of the simplest one is just DC offset. If DC offset is sensed at the speaker, it will cut back the power supply. It's not a very fast shutdown, and it's for situations where you've got some DC, but it's not very high, and it's not going to take out a speaker quickly. It's if you leave it there for too long, this voice coil might heat up too much and it'll melt. But it takes a while. The other sensing thing, or one of the other sensing things I have, is I have a little current transformer on the power supply power transformer, and what that thing is used for is if there's any imbalance in current between the positive power supply and the negative power supply, it shuts the power supply down immediately. And so if you have a catastrophic failure where an output tube shorts out, for example, or somebody pulls out an input tube or a driver stage tube or anything like that, that results in basically the speaker seeing the rail voltage, that current sense transformer picks that up in about 250 milliseconds, and it shuts the power supply down immediately. Now, if you got a lot of energy storage capacitors, which I do, effectively you've got to dump the energy out of those. But that's you probably don't want to use the energy storage that's in the quad Z to power a very fragile voice coil, because you do have that energy storage. But if you have a good match between a practical speaker and a power supply that has as much energy storage as the quad Z, you're going to be okay. And if you have one of the lower powered amps that doesn't have as much energy storage, you'll be okay with a smaller speaker. But and that 250 milliseconds I mentioned, it actually has to be. It could be made shorter than that, but it has to be long enough so that the amplifier can do its full 20 hertz or even 10 hertz into 4 ohm speaker. And if you make that shut down too fast, it'll shut down the power supply when you try and put low, real low frequency through a low impedance speaker. So you have to, you have to kind of strike a little compromise there. But as it turns out, it's not a problem. I mean, we haven't had we haven't had cases of fried speakers, where reasonable matches were made between speaker and amplifier.
So, yeah, so that goes kind of to the next question is how do you best match speakers and your amplifiers?
There aren't the severe issues with matching that you have with with the traditional OTL, because these amplifiers can drive so much more peak current than a traditional OTL amplifier. Now, the one caveat I have to mention, and that's true of any single-ended amplifier, and I did mention in my talk, is the problem with a single-ended amplifier of the non-symmetric drive. So if you're going to match a speaker to any single-ended amplifier, I don't care whether it's transformer coupled or ZOTL or whatever, you do have to be careful with that. But for the push-pull amps, no. I've, Rick and I have heard it, some of our clients of all things have even powered Apogee speakers with, with the Quad Z, and they claim that, oh, it works great, even though, we don't recommend it. But apparently you can do it. It's just not exactly something we would recommend, but there are specific amplifiers that are designed to drive those speakers. And the Quad Z is designed to drive a lot of hard to drive speakers, but it wasn't designed to drive that one. But people still do it, and do it successfully, believe it or not. So okay. Does that answer that, or?
Yeah. Next question, do you see new components on the horizon that could bring down the cost of your ZOTL amplifiers?
This is one of the things that Mark has been working on, and some of the people that work for him have been working on very successfully. In principle, the ZOTL is, switching power supply technology. And, the Chinese make power supplies that produce 50 watts you can buy them for 15 bucks. And the ZOTL technology, it incorporates a lot of the same stuff. So, obviously tubes are going to be more expensive than, you're not going to get down to $15, but you can actually go, there's room to go a long way. Of course, mass production is always going to be an issue. We don't, there's not enough people buying tube amplifiers to, get into, the mass production that, the Chinese can do with $15 power supplies. But, but there are opportunities, and Mark has been able to lower the cost on, some of the things that they're making quite dramatically. And they're still working on that. So.
Very good. That's all the questions I got in the chat. So if anybody wants to open up their mic and ask David a question, now's a good time.
Hi, David. It's Anthony. You mentioned the atmosphere amps earlier in the presentation, and I was just kind of looking at some of the topologies out there, and obviously cyclotron being one of them. I don't know how familiar you are with that circuit, probably familiar, but generally speaking, maybe talk a little bit about the differences between cyclotron and the Futterman circuit, if you could.
I think if you do the AC analysis, they're pretty much the same, believe it or not. if you replace power supplies with grounds, and which is what you do in AC analysis, you basically have two tubes in series. You have a push and a pull tube in series, and the cyclotron, the way they arrange the power supply is a little different than the way they do it in the Futterman. The Futterman, it's a little more obvious that the two tubes are in series. In the cyclotron, it's not so obvious, but when you do that substitution with the AC analysis bit, it comes down to, yeah, they're kind of in series too. So I think the biggest difference between the Futterman and the which are based on beam power tubes now, or were, and the atmosphere or the cyclotron, is the cyclotron is using the low impedance diodes. So you can get by with a lot less feedback. And I think atmosphere may even claim they don't use feedback. I'm not sure, but I think they've claimed that. I don't know what their output impedance is. But the tubes themselves, they're dual triodes, the 6AS7, and I think the plate resistance on each triode half is 250 ohms. And in parallel, you parallel the two sections, you're down to 125. And then you put a whole bunch of tubes in parallel, and you divide that by the number of tubes you have. And then again, since the tubes are, when you do the AC analysis, the tubes can actually be considered being in parallel for that. So you can actually divide the impedance down some more for that. It's certainly, with atmosphere's bigger amplifiers, it looks to me like they probably do, if no feedback was used, they probably could get down to, impedance that would, couple nicely with the 8 ohm speaker, and maybe be down around 8 ohms or, somewhere in that range. So I've never measured, one of the atmosphere amplifiers, but they certainly, they have a big following, and so I would take it to mean that, they've been successful and they've made a lot of people happy over the years with their amplifiers. So I've heard horror stories about tubes blowing and speakers blowing, but that's something that because I don't think they have any protection besides fuses. So.
Yeah, they're completely direct coupled. They are very low feedback. I think the most any of their amps uses is 2 dB, and most of them are 0. And I know that you mentioned the Futterman circuit early on had about 30 plus dB or something along those lines. I think the H3 circuit, which my friend Roger Majeski was using as a basis for designing his last OTL amplifier, had 60 dB of feedback. I think there was a patent on that, but I wanted to ask one more question, and then let some other folks ask. But what are your thoughts on Class D amplification these days? Knowing that Ralph Carson just came out with the Class D amp himself, so just kind of curious about that.
I have not heard a good one. Now, don't interpret that I've heard a bunch of them and they were all bad. What I did hear was a cheap one. It was like $20, and it was really pretty bad. I have not listened to one of the ones that's respected. So I don't know. I don't have an opinion on it right now. I can't form an opinion on one that costs $20. It's not realistic to do that. In fact, an amplifier that you could buy for $20 that put out, 5 watts, or, well, I claim 20 maybe, but that's pretty miraculous. Anyway, if it worked at all, and it did, but it just, boy, when it clipped, it really got nasty. and it didn't sound good, even aside from that. But for $20, you're not going to get energy storage, which is critical to good sound, and it's just. So the bottom line is, no, I haven't listened to them. At some point, I will. Somebody will have one, bring it over, and I'll put it on my speakers, and I'll be able to get a better idea of whether it sounds good to me or not. So yeah, someday. But right now, I haven't. I'm not to a point where I can form a realistic opinion.
What kind of speakers do you have, and what kind of music do you listen to?
Well, the speakers are the Merlin speakers, but I've done some things to them. First of all, I've got some 15-inch woofers that I made using high excursion woofers that Audio Express at one time sold. And those I came up with a passive crossover so that I drive those with the same amplifier as I drive the Merlins. The other thing I did with the Merlins is they have a peak, and it's quite a large peak around 700 hertz. And I did a passive network to suppress that peak. And again, because it was passive, it really killed the efficiency. The efficiency wasn't great to begin with, but now it's really bad. It's down in the low 80s, maybe 82. But I'm still driving them with a no feedback triode ZOTL that has only 10 watts of output, and it does amazingly well. Driving those horribly inefficient speakers, including the with the big woofers. Now the woofers are fairly efficient. I think they were rated around 90. That's what I have in my main system, and I think it sounds pretty good. It's not certainly the best speaker in the world. It's decent with the changes I made, because now it moves air, which it didn't do before. The little 6.5 inch so-called woofer it just became distorted if you put any bass through it. And now with the crossover, I've taken the bass out of it, or the deep bass anyway, so it doesn't get into trouble like it did in its normal state. So it's decent. It's not it's not competitive with the very finest speakers, but it does okay for me. And let's see, type of music, pretty much everything. I spend most of my time listening to classical, opera, but I'm happy listening to jazz somewhat, and rock and roll, and folk music, and all kinds of weird stuff. I use most of my music is on open reel tape. At least most of the music I listen to is on open reel tape. Most of those are like quarter track tapes that were made back in 40 years ago or more. Some of it's failing, some of the tape is fine. But as far as my opinion on tape versus LPs versus CDs, or servers, I've heard the good and the bad and the ugly out of all of it. So I'm not one to say, oh, you got to have tape. I wouldn't encourage anybody to go down that rabbit hole if they weren't already there, because they're keeping tape decks working is if you got a lot of spare time and money or whatever, okay. But they can sound terrific. And as it turns out, if I'm not just taking the easy way out, playing the FM radio, more often than not, I'm listening to open reel tape, or LPs is probably second. and music server maybe third, and CDs. I don't have very many of those, so I don't listen to those. Probably less than the other media, but not because they sound bad necessarily. It's just that I don't have that much music on them. So that's kind of a rundown on all that, I guess.
I have a question. You mentioned a Shostakovich string quartet. What is it about that makes it a test piece?
It's the music is kind of, you know, it's kind of dissonant and kind of you have to, with something like that that's not like I can't describe it as you know, real tuneful. It's more you know, dissonant. It's just you're depending on the sound of the instruments and the musicians to carry the day, in my opinion. It's just your brain has to kind of you know, go through the musicians to hear what they're doing, and it just seems to take a higher level of reproduction quality to be able to do that with the atonal type music that you know, that Shostakovich did a lot of. If done well, it's terrific. And the recording I have, it's on LP. It's on Louise Lear, I think Louise Lear. I've had the record for, you know, many years, but it's always been a very good test record for me because it just was a challenge. And my transformer coupled amps that I used to make, honestly, really didn't do a very good job with it. But the ZOTL works terrifically with it.
Any other questions for David?
Yes, David, this is Larry G. Thank you for speaking to our group. I know that there's an amplifier product, an LTA product called the Z10E, which is an electrostatic headphone amp and the speaker amp. Can you talk a little bit about any design challenges you had with that, and what makes that amp special?
Well, probably Mark did most of the design challenges with it, because, you know, after the you know, the fundamental simple, you know, the basic ZOTL circuit. You know, originally it was just a kind of a not really intended to be one of the higher end, you know, products. It was it used the EL 84 tubes, you know, modest power, you know, nothing, you know, terribly special. Using it as an electrostatic headphone driver was actually quite easy to do with it, simply because you got the push-pull tubes, and with the ZOTL, I tend to operate pretty high voltages, and the voltage was high enough on those to you know, key in very nicely with driving you know, most of the electrostatic phones that are out there. So it really is a matter of, you don't really do very much, just come off the plates of the output tubes with some DC blocking capacitors, provide a high voltage bias supply for the headphones, and you're pretty much done. So Mark's enhanced it from my original cheapy design, which didn't have, well, it had auto bias, but it didn't have the real high precision DC nulling circuitry that my other amplifiers had. So Mark added that. And so now you don't have to be so careful matching tubes to, not have a problem with some DC offset at your speaker. So, Marcus and his crew have tweaked it a bit from, the original, design that I, provided. And Mark has added a lot to these, that one as well as all the other ones where he's worked very hard on, wide dynamic range volume control and, some of the remote control of all the input functions. And I had nothing to do with any of that stuff. That's all, was done by Mark and the LTA guys. What I provided to them was the basic, building block of the ZOTL circuit, and they've enhanced that with all the, the extra features that make people happy. My opinion on the remote control thing was, well, people should get up every 20 minutes. It's good for their cardiovascular. Get up every 20 minutes, change the record or whatever. Forget the remote control, but Mark's made it appealing to a lot more people that don't want to do that. So,
So one of the things that David it might not be so clear. So he runs the tubes at 250 kilohertz, but the voltages are generally double what the rated voltages of the tubes. So I think the Quad Z runs at 1200 volts or something like that, or ZOTL 40.
Maybe a little more, yeah.
Yeah, the ZOTL 40 runs at 1000 volts. The Z10 products run about 750 volts. So, and it's a plus 750 and a minus 750. So basically you have a 1500 volt voltage swing. And for an electrostatic, 1200 volts voltage swing is about the minimum. And so, but anyway, all the ZOTL amps have double the dynamic range, if you will, because we have double the voltage swing. So it was pretty straightforward because basically the tubes are in ZOTL mode. We're not using the output stage for the electrostatic. We're just kind of borrowing the signal straight off of the tube, and then we put it through a cap and resistor so that it's extremely low current and drives it doesn't have to have a lot of current to drive the electrostatic headphone. But because there's really hardly anything in the electrostatic path, there's even less than what the speaker sees, you get a really good quality electrostatic driver.
Well, thank you.
I might add that I don't recommend this for safety reasons, but some of my amplifiers, like the ZH270 that Larry has, they can drive. You can use those to direct drive electrostatic speakers that want to see maybe 3000 volts because the voltage is so high in the ZH230 and the Quad Z for that matter, that you can do that. I don't tell people to go out and do it simply because I don't want somebody to electrocute themselves, but it does work.
Something else. So when you so if you listen to a regular tube amp, you get that tube warmth, and there's varying degrees of it with different tube amps. But that warmth, which isn't part of, it's intermodulation distortion in the transformer, covers up the micro detail. And so one of the first things when you listen to a ZOTL amp versus a regular tube amp is you have all the detail of a solid state amp with a nice tube tone. You still get a little bit of the warmth because it's a tube driving it, but you don't get anything that wasn't part of the recording. And that's the biggest thing. Another thing, it's super dynamic because of what we talked about earlier in a typically classical piece where it's very quiet and all of a sudden it's thundering. This does this very easily. Then another thing is there's no hum. They're totally silent. You have a very, very black background and the music just comes. So it sounds very, very clear. And I'm not sure if that's a ZOTL or just the way David designs amps. But anyway, those are kind of you get a lot of, it results in, I'm not sure if it's ZOTL versus a regular tube amp, but you get a lot of extremely well imaged sound stage. It has a depth, it has a very big width, and you can really tell where the performers are located in that sound stage. So that's one of the things our amps are noted for. But that could just be because David's a really good tube amp designer and has nothing to do with the ZOTL part. I don't know. So we just get them. We get them, and then we change the components and wrap a digital control system around it that doesn't actually, the circuit's completely different. The analog just goes to the relay contacts, and we have been most of the labor. David stuff has a lot of wound parts, so if you buy 1,000 of these parts, you can get someone to actually make them with a machine, and that saves a lot of labor. So so in the future, we hope we see our products, some of them going down in price because of the labor savings, but it's something, it takes a long time. We've been working on it for a year or so, and we got another 6 months or a year worth before we get everything.
Very good. All right, we have a couple more questions in the chat, and then maybe we'll wrap it up because we're coming up on 2 hours here. One question had to do with the wide dynamic volume control. Can somebody speak to that?
Yeah, so we're using stepped attenuator, but relay controlled stepped attenuators. So we used to use linear steps. We had 1,000 steps, and you could pick out of those 1,000 steps values and simulate a logarithmic response, which is of course what the ear is. So they were very close together at one end, and then they would get 5 steps apart, 10 steps apart, 15 steps apart as you go. Then we switched to a actual logarithmic one, and we have a half dB, but under a half dB, you start running into the plus and minus 1% of the resistors, because the smaller steps are much, much smaller when you use true logarithmic, and that provides a lot more detail or a lot more control at the very low levels. So we have something now that's about 100. We use 8 bits. It's got about 256 levels, but it's logarithmic, and so we take about 200 steps out of that. And you can move up or down. You can have the top 100 steps, the bottom 100 steps, the middle one, or you can have all 200. If you have all 200, you might have to go 30 or 40 steps before you hear anything. But some people have huge amps with very efficient speakers, and they can hardly use any part of the volume control. So this way, we allow you to kind of shift in the range so that you get the most steps in the particular listening. The combination of your efficiency of your amplifier and your speakers. So, but it's basically, we use tantalum resistors, we use little tubular, we use nichrome resistors. There's a huge array. There's actually more in the surface mount than there is in the through hole. And so anyway, we've been trying, we use and our preamps, we use the tantalums, and our integrateds, we tend to use the nichromes. But of course, everything we do, we have to listen. There's a lot of listening that goes on, which takes a lot of time. So we have a bigger staff than just David. We got 10 people, and so we can do a lot more listening and try a lot more different components than David was able to by himself. So that's been one reason why we're able to make some of these amps sound so good. Because they're really platforms for the tube quality. If you have really good tubes, it just gets better and better. It's also a platform for the component quality. So over the years, we've changed all kinds of different resistors. We even have some audio note resistors in there because they're tantalum, and you get this mid-range detail that you don't get with any of the resistors. Anyway, I hope that answered your question.
Yeah. All right, one last question and we'll wrap it up. Highly interested in hearing about the sonic and functional differences between the LTA integrated amps. Heard the Z10 and admired it. How do the Z40 Plus and the Ultra Linear Plus differ from it, besides simply tubes employed and power ratings?
Good question, and it's a very simple answer. The Z10 used a linear power supply, an excellent one, but it's no match for David's switching supply design for audio that he continues to improve and improve even to this day. And once we say, you know, I love the Z10, but once you get a Z40 or ultra linear, you're never going to listen to it again. It's really a huge improvement because of the power supply. When I started in this, I thought, you know, you got an amplifier and there's a power supply off to the side, and it doesn't, you know, it's great if it's good, it's great if it's better, but David's taught us that the music goes to the power supply, and you need the best power supply that you can, and the quality of the power supply might be 70% of the sound quality. In phono preamps and DACs, it might even be a little higher. Anyway, so that's the main difference, is David's power supply, which is much more expensive to build than a linear power supply.
Very good. Well, sure appreciate your time and all this great information, and I'm sure enjoying my ZH270. It's a great amp. So thank you very much.
Okay, thanks for letting us talk.
Yeah, thanks for having me give the spiel, and I hope that you know, people got something out of it.
Absolutely. All right. Well, take care.
All right, thank you.
All right. Bye.
Bye.